Chapter 6 is radicals and exponents. More of this chapter than in previous chapters will what we do now really make a difference in the next one. This chapter and the next chapter are really tied together. The rules you get here will be essential in what we're doing in the next chapter. You don't get this stuff down, you're really going to struggle with some of the stuff in there. We're doing logarithms and exponentials, and this is dealing with radicals and exponents in this chapter. If you don't have the rules down here, you're not going to get them. It's going to really make the next chapter extremely difficult. It's one of those things that really, math, as you know, anyways, builds. This is one where there's a straight tie-in. Okay, I cannot emphasize enough that you get the rules down. You get them memorized. You have any formulas, you get them memorized. You have to know them. You have to understand them. You have to be able to manipulate exponents. You have to be able to simplify radicals. You have to be able to go back and forth between radicals and exponents. You've got to be able to interchange both of them. The rules and stuff that we get down in this one, you've seen a lot of them before, but not all of them. But you really have to have them down. You have to be comfortable working with exponents and working with radicals and interchanging the two. And you have to have the rules down well, or the next chapter is really, really, really difficult. This is also something as you progress into the next course is an important one. Okay. Today we're dealing with multiplying and dividing radical expressions. A radical consists of basically two parts. You have the radicand, which is the thing we are taking the root of, and then the index, which tells us what root, square root, cube root, or fourth root. Normally, if you don't write a number, the number you don't write is you don't put 1 or you don't put 0. If you're adding or subtracting plus 0 or minus 0, we don't do plus or minus 0. We're lazy because plus or minus 0 doesn't mean anything. If we have an exponent to the first power, x to the first power, we don't write x to the first power. We don't write 1 times something. We just put that number down. We don't write 1x, we just put x. Because if you have x by itself, how many do you have? You have 1. Putting the 1 in front is redundant. Okay, having something to the first power is redundant. So we don't do that because mathematicians are lazy. Think of all the acronyms that you used in geometry. Rather than writing out sine angle side, you put just SSS or SAS, right? We're lazy. We come up with symbols for freaking everything. Okay, it's just who we are. We like to work the problem, but we don't like to write. And so we come up with all kinds of shortcuts. We don't write things that we don't feel are necessary to put down, ones that are given. The only time you do not have a 1 or a 0 that is not written there is with radicals. A square root by itself has the index of 2. We don't write a 2 with a radicand. We don't write the index of 2. That's the only number we don't write that's not a 0 or 1. It's only with square roots. And there is no single root. There is no index of 1. You don't have that. That doesn't exist. It's not a concept we work with. Okay? So we don't write an index of 2. If you see a radical by itself, ooh, that means it has an index of 2. This will be much more important later on in some of the stuff we do, but it needs to be introduced at this point. And the index tells us how many times we're multiplying things. Square root, what times itself gives us that number. A cube root, what number cubed gives us that. Okay, they're the opposite of the powers. And it's a very important thing we're going to be working with. Two of the formulas you're going to be working with today is if I have two things with the same, two roots with the same index, or I'm multiplying, it is the root of both of those multiplied. And this goes in both directions. I can split things apart. This is how we did simplifying radicals. You rewrote it as, we took the number underneath, rewrote it as two things multiplied, and then split it into two radicals. That's how you simplify a radical. Gracias. Same thing goes true for fractions. If I have a radical, if I have a root of a fraction, it is the root of the numerator over the root of the denominator. Also, if I have two separate roots, I can combine them into one as long as the index is the same. Okay, the index needs to be the same in order to be able to combine them up or split them apart. Okay. So let's take a look at some examples here. Cube root of -8. Normally, when we have a negative underneath a radical, you can't do it. We have a couple of exceptions. One, if you have a square root, the square root of the negative is I. We did that last semester. You won't see that a whole lot in here, but you might see it from time to time. And then you can have a negative root of if it's an odd index. So the cube root of -8, well, the cube root of 8 is 2. Cube root of -8 would be -2. Because what times itself 3 times gives you -8. -2 times -2 times -2. Obviously, you can use your calculators when you're doing this, but there also are some numbers you should know and understand and be able to do without your calculator. The more you can do without your calculator, the better off you're going to be. Okay. I teach my AP calculus class with almost no calculator usage whatsoever. They can use it all the time, and there are certain things that they can when they take the AP test, some things that they can use it on some of the tests, not use it on other parts. I teach without the calculator as much as possible, so they're capable of doing almost everything. And you understand it better if you can do it. Now, if you need to pull your calculator out, you need to do it. Square root of 0.04. Okay, there's a trick to this when you have decimals. Okay, the square root of 4 is 2. The square root of 0.04 is not 0.02. How many digits do I have after the decimal place? 2. So when I take the square root, I'm going to have half of that. I'm going to have 1 digit after the decimal place. So this would be 0.2. If you're taking a square root, you'd have half the decimals in your answer. Right? Does that make sense? So if you have 0.25, it would be 0.5 would be what your square root would be. Cube root of 1/27. One way you can think about this, it's the cube root of 1 over the cube root of 27. If you want to think about it this way and break it down into 2 separate cube roots, sometimes it makes it easier. Or you can just do the cube root of the numerator in your head. Think about it that way. Cube root of 1, well, the root, any root of 1 is the easy one, it's 1. Okay. So I get 1, cube root of 27 is 3. And you should know a few powers. Powers of 3s and powers of 2s are the ones you're going to need to really know a lot of. You should know cube root of 27 is 3. You should know, and the next one, the 4th root of 81 is also 3. Ones you should start to learn and know by heart. Okay. Let's pause for a minute before we get to this next one. I'm actually going to go back so I have a little more room to write using your calculators to do this. On your calculators, you have radical keys. You have keys that let you take these square roots, or cube. Square root's easy. That's built in. You will have on your calculators, all calculators have a square root key somewhere. It's either there, or you might have a key that's like x squared, and above it where you have to hit the shift would be the square root key. That's easy. That's square roots. Cube roots, on the other hand, or 4th roots or 5th roots, a little more complicated, but you can do them on your calculator. You have 1 or 2 options for your keys. They will both look like something like that. Okay. Here's what you do. If I want to take, for example, the cube root of 8. What you do is you type it in. You hit the 3, type in 3, and then you hit your root key, X, Y, and it will look something like that. Each one's a little different, but it'll look something like that. And then what you're taking the cube root of, and then answer or execute or whatever the command is for your particular calculator to solve the equal button, different calculators, different things. And it should give you 2. And this is one you should know by heart. The cube root of 8 is 2, because if you're not sure how to do it on your calculator, you can type it in one way. If it doesn't work, you turn the numbers around and type it in the other way and see if it gives you the right answer. Okay? If you're learning how to do something new on a calculator, do something you know by heart and try it. If it doesn't work, try switching the numbers around, making sure you know how to do it. Okay? It's one of those things that I did whenever trying to teach kids how to do something we're done on a calculator. That's one of the things I recommend. Do something you know how to do without your calculator. Use your calculator to do it, to check to make sure you're getting it right. Because don't put in numbers you don't know, because you might be doing it wrong and getting an answer. Oh, this is how you do it. You don't know. Do something you know. Okay? But that's how you do that. Once again, you should try to be able to do it all by hand first, without your calculator as much as possible. I'm not saying you can't use your calculator. I'm not saying there aren't times when you need to use your calculator or should want to use your calculator. Okay? But you should be able to do as much as you can without. The more you can do without, the stronger you're going to be. Okay? So next one, square root of negative 49. We did this. Square root of 49 is 7. Square root of a negative is I. Fifth root of negative 32. Well, I happen to know my binaries. I happen to know that 32 is 2 to the 5th. Because that's an odd power, it's negative 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 2. 32 is 2 to the 5th power. Square root of 25 and to the 4th. Okay, we can think about this in a couple of different ways. We've got the square root of 25 times the square root of n to the 4th. So that's actually a pretty easy one. Square root of 25 is what? 5. Square root of a variable. Okay, what is the index on a square root? It's 2, right? Square root has an index of 2. Take the power of your variable, divide it by the index. What do you get? 4 divided by 2 is 2. That means this is n squared. If it goes in evenly, woo, you like that. Trust me. Okay. If it doesn't go in evenly, it's a little bit trickier, but it's still really not that hard. Okay. So, for example, on the next one, square root of c cubed and d to the 9th. Well, my index once again is 2, because I'm taking the square roots, but neither 3 nor 9 are divisible by 2. You still do the same thing. Only you will have a remainder, and your remainder stays inside the radical. So you pull out what you can, you leave behind what you can't. So I look at this, I'm going to have a square root of c cubed, square root of d to the 9th. Here's what I do. I take 3 divided by 2. 3 divided by 2 is 1 with a remainder of 1, right? So this would be c to the first outside, c to the first left inside. It's strictly the c cubed portion. Okay. 9 divided by 2 is 4, remainder 1. So that means I have d to the 4th and d to the 1st still inside the square roots. Make sure your square root covers the whole thing. You'll notice sometimes, I don't always do it, but sometimes I'll pull a little hook at the end of my square root or cube root that tells me, lets me know where it ends. Helps me not make it shorter and shorter every time. Kind of like doing the quadratic formula where it gets shorter and shorter, and at some point it still includes parts that should be in it. Okay. Let's take a look at this one. Same idea. Our index is 3. So I'm going to take 12 and divide it by 3. 12 divided by 3 is 4 with a remainder of 0. So I don't have anything left behind for the a's. I have a to the 4th. Okay. I take 15, divide it by 3. 15 divided by 3 is 5 with no remainder. B to the 5th, and nothing left inside. It goes in evenly. It's a perfect root. Those are perfect. That's a perfect cube root. Okay. Next one. I do the x's, I do the y's. 16 divided by 4 is 4 with no remainder, so x to the 16th. That's nice. I get x to the 4th for that. Then I take the 4th root of y to the 5th. 5 divided by 4 is 1 with a remainder of 1. So I have a y to the 1st that I pull out, and then a 4th root of y to the 1st left inside. Okay. I think that variables are the easiest part. They go in if they're perfect. If they're not perfect roots, they're easy. And I think even if they're perfect roots, they're easy. 5th root of 32. Well, we already did the 5th root of negative 32. So the 5th, yes. Question. No, it's okay.
Why does the y on the last one go 4?
It doesn't. This is for the root.
Okay, so are we supposed to put it like that or just leave it?
You always have you never lose your index. Okay, now I didn't write the index with the square roots because there is no index. But this is a square root, so it's here. These are this is the first one we've had left behind. If I do this, let's do this. I got x to the 4th for the 4th root of x to the 16th, right? And then for the y, I've got y to the 1st. Let's do this. I got y to the 1st, and then I had the 4th root of y to the 1st left behind. Does that help?
Yeah.
Does that help a little bit? Make it a little clearer?
I thought
Welcome to my world when I'm grading your tests. Sometimes, because I know what I'm looking for, I look for that. Where is the radicand? Where's the index? And sometimes it's hard to tell if you have it as an exponent or if you have it as an index. A little space kind of helps a little bit. But I usually know what the right answer is supposed to. I know what the right answer is supposed to look like, and if what you have looks close enough to that, I will often take it. It depends upon where I can usually tell when it's right or it's wrong, even if it's hard to read.
All right.
Doing it long enough.
No,
No, you don't because on square roots we don't write the 2.
okay.
We don't write the index. But if you have cube roots and 4th roots and 5th roots, you do that. Okay, so let's do the next one. 5th root of 32 is 2. We did the 1st root. Like I said, you've already got some we've done. 5th root of 32 is 2. So for this portion, I get 2. And then for the end of the 7th, 7 divided by 5 is 1 with a remainder of 2. So that means I have m to the 1st, and then I have a 5th root of m squared, because that's my remainder was 2. 7 divided by 5 is 1 with a remainder of 2. So any of my remainders I put outside. And this is the first remainder we've got that's been more than 1. Okay. Questions? I think that's fairly straightforward. Your turn, do those. And yes, the last couple of problems look daunting, or actually down here at the end, there's more terms than I've done. Not a big deal, just do them one at a time. Okay, so let's do these. First one, 4th root of 81, that's 3. I actually had that same problem on the previous page. Cube root of negative 27 m to the 6th. Cube root of negative 27 is negative 3. 6 divided by 3 is 2, so that's m squared. The next one, 4th root of x cubed cannot be simplified. 4 does not go into 3, so the 4th root of x cubed stays right there. 4th root of x cubed. You can't do anything to that. You can, however, simplify the y to the 8. 4 goes into 8 twice, so I pull out a y squared. Square root of all of these, square root of 49 is 7. And then because those are even, I just take half of those powers. A to the 6th, b to the 7th. Cube root of 81 is not doable. So here's what you have to do. Simplify the radicals. Now we did this with square roots last semester. You can do this with other roots as well. 81 is 3 to the 4th power. So I can rewrite 81 as 3 to the 4th power, and then I can do that the same way that I do the variables. Okay, so 3 to the 4th, cube root of 3 to the 4th, 4 goes into 3, sorry, 3 goes into 4 once with the remainder of 1. So for the 81, I have a 3 out front, and then a cube root of 3 left behind. That's strictly for the cube root of 81. Bless you. N to the 6. 6 divided by 3 is 2, so I pull out an n squared. Bless you again. With nothing left behind because it goes in evenly. 8 divided by 3 is 2 with a remainder of 2. So that means I have p squared and p squared. Not a really good 2 there. It's a better 2. I think the ones with the exponents on variables are the easy ones. I really do. The numbers are where it gets hard. 9 divided by 8 is a 1, remainder 1. So I have a to the 1st, 8th root of a. 16 divided by 8 is 2, goes in evenly. So I have b squared, no b's left inside. 13 divided by 8 is 1 with the remainder of 5. So I pull out a c to the 1st, and I have a c to the 5th left inside. And the last one, this is actually really easy. Really, really easy, because it's divided by 10. So your 10's unit is your power on the outside. Your 1's unit is the power left on the inside. Right? 10 goes into 12, once remainder 2, once remainder 5, twice remainder 9. So I have x to the 1st, y to the 1st, z squared. And then the 10th root of x squared, y to the 5th, and z to the 9th. Yeah, dividing by 10 is easy when you're looking for your remainders. Divide a number by 10, it's the 10's unit, and then the 1's are your remainder. It's easy. Questions? Okay. Multiply and simplify each radical expression. Yeah, this can get a little hairy sometimes. Okay, sometimes it can, sometimes it can't. Here's the deal. Each problem needs to be looked at individually. Sometimes it's better to just multiply and then simplify. Sometimes it's better to simplify first and then multiply. I look at the first problem here. I have the 4th root of 2. I cannot simplify that. I have the 4th root of 8. I can't simplify that because 8 is 2 cubed. But I can multiply them together and then try to simplify. So this would be the 4th root of 16. 2 times 8 is 16. And 16 is 2, 4, 8, 16, 2 to the 4th power. So this would be 2. That's my final answer. Next one's where it gets fun. Okay. I have several choices here. I can take 45 times 35 and see if that's a perfect square root, or see if it's even one I want to work with. The number I think is going to be way, way, way too big. 45 times 35 is 1,575, which I don't think is a perfect square root, but I will try to take the square root. Nope, it's not a perfect square root. That sucks. 39 point something or other. And we don't want decimals, we want radicals. We want exact values. A decimal would be an approximation. In this class, unless you're told otherwise, you want exact values. So here's what I want to do. I want to see if I can simplify things first. Simplify things, particularly the numeric values. The variables are easy. I'll deal with them later. But the numerical values are where it gets hard. So I can work with this in parts. I don't have to do the whole thing all at once. What I can do is go, okay, 45 and 35. Let's see what I have. 45, and I'm going to do it down here. 45 is 9 times 5. Well, 9's a perfect square, right? That makes that nice. So for the square root of 45, I get 3 root 5, because I have the square root of each of these, right? Okay. But what about 35? Square root of 35. 7 and 5 are the only two numbers that multiply to give me 35. Square root of 5, square root of 7. Neither one of those are perfect squares. However, look at that. Because I'm multiplying those two numbers, right? Which means that I'll have, when I multiply them, the square root of 25. When I take these two and multiply these two things together, when I take this times this, I get the square root of 9. Square root of 5 times square root of 5 is the square root of 25, and the square root of 7. Now, there's more than one way to do this. I'm trying to break it down, but if you break things down into the smallest units possible, it will help you do it easier. Okay? So, numerically speaking, when I multiply those together, I have the square root of 9 and the square root of 25. And the square root of 9 is what? Square root of 25 is 5. So I have 3 times 5, which is 15, root 7. That's strictly the numeric portion. That's the hard part. Really, that's the hard part. The variable portion is a piece of cake. The numeric portion is where it's really hard. And technically, let's make this more than one step here. Let's do this. 15 square root of 7. And just leave the variables underneath, but go ahead and put them together. X to the 5th times x to the 1st is x to the what power? 6. 6 power. Y cubed times y to the 4th is y to the 7th power. I add the exponents. I've already simplified the numerical portion. Now I need to simplify the variable portion. That's easy. What's 6 divided by 2? 3. Remainder of? 0. 0. So that means I have 15 x cubed for that. Still have my square root of 7. No square roots of x. 7 divided by 2 is 3 with a remainder of 1. So I have x cubed out front. Or sorry, y cubed out front. And a y still left behind. One way to do it. One way to do it. There is more than one way to do this. Second one, I'm going to do it a little differently. I'm going to go ahead and just multiply it. I'm not going to try to simplify it first. Part of the reason is that 18 and 6 aren't that big, and I got a funny feeling about 18 and 6. But I do 2 times 3, they're out front, so that gives me 6. Square root of 18 times 6, which is 60 plus, oh, I forget, 108. That's what I get. And then I do my variables. A cubed times a to the 1st is a to the 4th. B squared times b 7th is b to the 9th. Okay. Now I can start simplifying. And part of the reason I did this is 108 is a whole lot easier to deal with than 1575 that I would have gotten with the 45 and the 35. It's easier to work with. So I look at 108. I go, okay. 108 is 9 times 12, right? Nine times 12. 9's a perfect square. Can I simplify 12? Yeah. 9 times 4 times 3, right? So if I have the square root of 108, that's the square root of 9 times the square root of 12, square root of 9 times the square root of 4, square root of 3. Which means that I have 3 times 2 times square root of 3, which is 6 root 3. That's what the square root of 108 does. And I did it off to the side. I didn't do it as part of my problem. I did it off to the side. Square root of 108 ends up being 6 root 3. So this is 6 root 3. So I pull out a 6. What do I do with the 6 that's already out there? I multiply it. So I have the 6 from here, and the 6 from here gives me 36. And then I still have, underneath the radical, root 3. And now I do the variable portion, and that's easy. Half of 4 is 2. So I have a squared. And then 9 divided by 2 is 4 with a remainder of 1. So that means I have b to the 4th and b to the 1st left underneath. So it's not pretty. It is doable. Variables are easy. It's the numeric portion that's a pain. Relatively speaking. Okay, your turn. Do those. Okay, so let's do these. First one, multiply everything outside, everything inside. It's the easiest way to do this one. 4 times 3 is 12, and then I get the square root of 16x squared. Okay, and that's actually not that bad. Square root of 16 is 4. 4 times 12 is 48. Square root of x squared is x. I get 48x. Radicals all go away. Next one, I would do the same thing. The numbers are small enough. Leave the square roots and square roots. Stuff outside. 7 times 2 gives you 14. Square root 3 times 6 is 18. X cubed. And then y squared times y is y cubed. So you want to do that. Square root of 18. Like I said, the numeric portion is always the most difficult. Square root of 18, square root of 9 times the square root of 2, because 9 is a perfect square that goes in 18. So square root of 18 is 3 root 2. I already have the 14 out front. I have the 3 here. I have to multiply them. 4 times 3 times 14, that's 30 plus 12 is 42. Square root of 3, square root of 2. Okay. And then I have to do my x's and y's. 3 divided by 2 is 1 remainder 1. I have x to the first outside and x to the first inside, and the same thing with the y. Next one is cube roots. Now, 50 is a fairly large number to deal with. If I were doing square roots, I would take out, but I can't do a square root of 50, cube root of 50, and I can't simplify it. If I look at my cubes, none of these numbers divide evenly into 50. So the ones that I have smaller than 50 don't divide evenly into 50, so I can't simplify the cube root of 50. I have to multiply them first. Okay, so I have the cube root. Let's see, 5 times 15 is 75, so 750. And then I have to do my variables, and I have b squared, c to the 5th, and d to the 6th. Now is one of those divisible by one of these perfect cubes, 125. 125 does go into 750. We don't know how many times. 750 divided by 125 goes in 6 times. So if I do this down here, the cube root of 750 is the cube root of 125 times the cube root of 6. Notice I didn't look for perfect squares. Why? Because it's cubes, it's cube roots, not square roots. Cube root of 125 is 5. So that means I have a 5 outside and a 6 left inside. That is strictly the numeric portion. And now I do the variables. B squared, 2 is smaller than 3. I can't pull any b's out. So I have b squared. C to the 5th, 5 divided by 3 is 1 with a remainder of 2. So that means I have c to the 1st outside and c squared left inside. And then d to the 6th, 6 divided by 3 is 2 with no remainder. So I have d squared outside. And that's my final answer. We're almost there. Deep breath. Aren't you glad we didn't do this yesterday, the first day back? Okay. Once again, these problems are done differently depending upon the individual problem. I look at the first one, and its square roots, and my denominator is a perfect square. My denominator is a perfect square. I'm not simplifying first. I'm simplifying individually numerator and denominator. Because my denominator is a perfect square. And we're not allowed to have radicals in our denominators. Square roots, cube roots, whatever. We have to simplify and we have to get rid of them. Well, my denominator is a perfect square. I'm just going to take the square root of the numerator and square root of the denominator, and I'm going to go from there. So I have 25c squared. Square root of 25 is 5. Square root of c squared is c to the 1st. 49 d to the 4th, square root of 49 is 7. Square root of d to the 4th is d squared, half the power. And I'm done. I can't do anything else to this. 5 and 7 do not reduce. I can't reduce the variables or anything like that. I look at the next one, and I'm going, okay, my denominator is not a perfect square. I can simplify this the x cubed, but I don't want to if I don't have to at this point. What I want to do is instead think about this problem as being 1 square root. And can I simplify that fraction first? Yeah. What's 18 divided by 2? God, give you an easy one. Okay. X to the 5th divided by x cubed. What do you do to the exponents when you divide? You subtract, so that would be x squared. And this one's a perfect square. This is easy. Square root of 9 is 3. Square root of x squared is x, so this is 3x. I look at the next one, cube root of 21b to the 10th over 7 cube root of 7b. I'm doing the same thing. I'm simplifying first. Now I can, do you believe me, that I can skip the step of writing this one radical first and just go ahead and divide. They're both cube roots. I can just divide the numerator by the denominator and put 1 cube root there. So I end up with the cube root. 21 divided by 7 is 3. B to the 10th divided by b to the 1st is b to the 9th. And now I simplify this one. Cube root of 3. Can I do anything to the cube root of 3? No. What is the cube root of b to the 9th? B cubed. 9 divided by 3 is 3 with the remainder of 0. I can pull this out front. I can't do anything with that, so I have b cubed. Cube root of 3. Notice I always put the radical at the end. I did not write this as the cube root of 3 times b cubed. Why? Because I don't want to accidentally suck the b cubed back underneath the radical. Radicals always go last. Standard operating procedure, you write your constants, you do your variables, and then you do radicals. So everything that's not a radical is out front, everything that is a radical goes behind. You don't put the radicals in front and the other stuff behind it. It's really confusing. Okay? Your turn, do those. Okay, let's finish this up. So the first one, what I would do is, once again, go ahead and divide it first, simplify it. 63 divided by 7 is 9. So I have the square root of 9. So 9, not 6, 9. Let's just do an upside down one. Square root of 9a b cubed divided by b is b squared. And then simplify that one. The square root of 9 is 3. Square root of a to the first is still the square root of a. There's nothing I can do to that. Square root of b squared is b. So I have 3b root a. Next one, do the same thing. 54 divided by 2 is 27, right? Yeah. Square root of 27. X to the fifth divided by x squared is x cubed. And y cubed divided by y is y squared. So that's my first step. Now I need to simplify the radical. Square root of 27. 27 is 9 times 3. Square root of 9, 3. Root 3. Square root of 27 is 3 root 3. Square root of x cubed. 3 divided by 2 is 1, remainder 1. I have x to the first outside, x to the first inside. And the square root of y squared is y. So I have 3xy square root 3x. Okay, a little more complicated here. What I would do is I would divide it out first. 243 divided by 3 is 81. So I have the fourth root of 81. Now the c's are a little bit more difficult because the one in the numerator is smaller than the one in the denominator. I would still divide and reduce, but because it's bigger, your answer would be the denominator. Still subtract. 11 minus 3 is 8. But because I have the 11 in the denominator, I have c to the 8th in my denominator. And it's still the fourth root, still inside the radical. I haven't done anything to simplify that yet. And then I have d to the 6th divided by d squared. 6 minus 2 is 4. And it does go up in the numerator. D to the 4th. And now I simplify the radicals. And actually, it's not that bad because they're all perfect fourth roots. Fourth root of 81. 3 to the 4th is 81. Fourth root of 81 is 3. So I have 3. Fourth root of d to the 4th is d. Fourth root of c cubed, c to the 8th is c squared. 3d over c squared. And the last one, well, 81 and 16 don't reduce. Okay? In 11, I have n and I have d. I can't do anything with the variables either. But if I look, I go, oh, wait a minute. 16 is a perfect fourth root. 81 is a perfect fourth root. D to the 16th is a perfect fourth root. I'm just taking the fourth root of everything as it stands. Fourth root of 16 is 2. Fourth root of end of the 11th. 11 divided by 4 is 2 with a remainder of 3. So I have n squared, fourth root of n cubed, all over. Fourth root of 81 is 3. Fourth root of d to the 16. 16 divided by 4 evenly, so I just get d to the 4th. And that's my answer. These problems and many of the problems that we will have in the future in this chapter will look daunting, particularly when you're simplifying. But if you break it down part by part, don't look at the whole picture. Don't look at the forest. Look at the trees. Okay? Look at the individual parts. Individually, each part is easier than the whole. Really makes a real difference on doing these. Okay?